My goal in this video is to define a tangent plane to a surface. Before we get started, I could think about a surface like a hemisphere. What I want to do is find the equation of a plane that's tangent to my sphere. In the same way a line could be tangent to a circle or a parabola or anything else. It's like the 3D equivalent to finding a tangent line from Calc 1. But to start off, let's just think about a level surface. So I have a function on 3 variables, and I'm thinking about all the x, y, z's that give me the constant c as an output, so any level surface. And I'm imagining that I have a smooth path r. And so if I'm letting my level surface, c equals f of x, y, z, be represented by this hemisphere, then the path r of t is just some path on its surface. So maybe r of t is this curve, but I don't know anything about r of t other than the fact that it is smooth, so no sharp points, hop, skips, breaks, or jumps. So maybe this is r of t. And just for the heck of it, one more. And in a moment, I'm going to want to consider one point. This on a set of curves, or a better set, I'm going to imagine a bunch of curves that go through the same point. So for convenience, I'm just going to go on and draw this one going through a point that they all share. But r of t could be any curve that lies on the surface f of x, y, z equals c. Okay, so let's imagine curves that go through a specific point. So imagine our r of t passes through p naught, which will just be x naught, y naught, z naught. So that's that point I went on and put on all 3 curves because I knew I was going to want that eventually. So p naught, that point right there. And that's the point I'm going to want to end up finding a tangent plane to my surface at. Okay, well, let's just think about it. What do I need to find the equations of a plane? I need a vector perpendicular to my plane, and I need a point on the surface. Well, check. I have the point on the surface. Now I just need a vector perpendicular to the surface. And since this is a level surface, I bet you could go on and figure out what vector that is. In fact, pause the video and think about all of the vectors we've talked about. And see if you can think of what vector is going to be perpendicular to this level surface. Okay, well, I hope you thought of something. But what I want to do now is kind of derive this particular vector that we're going to need, that is perpendicular to this level surface. So I know that c is equal to f of x, y, z on the path I'm considering, because it's on the level surface generated by that equation. But I also know that the function f of x, y, z has to obey the chain rule for paths. So I'm taking the derivative of f of r of t, and in particular, I'm taking that derivative at a particular point, p naught, but I know the chain rule for paths says that this derivative is equal to del f of r of t times r prime of t. Well, this is my gradient vector. And this is the velocity vector, which happens to be tangent to the direction of motion. Excuse me, tangent to the path, tangent to r of t is pointing in the direction of motion. So if I was traveling this purple path from here up, big T is pointing this way. If I'm on the red path going this way, the direction of motion is going this way, and the green one's going this way. And if I think about it, it looks like all of those directions of motions, all of those velocity vectors, or the unit tangent vector, would lie in the plane I'm trying to find, right? That's tangent to the surface. Because in being tangent to the surface, this plane also happens to be tangent to all 3 curves I drew. In fact, tangent to every curve that could possibly pass through this point, p naught. Even better than that, taking the derivative of f of r of t, well, f of r of t is equal to c, so its derivative has to be equal to 0. Because I was really taking the derivative of a constant. And this establishes that my gradient vector is orthogonal, is perpendicular to the direction of motion. So that vector I was looking for, that's orthogonal to my tangent plane, is del f, the gradient vector evaluated at that point. So what's really nice about that, that's going to allow me to define tangent plane. Okay, so here's my definition of tangent plane. The tangent plane to the level surface C equals f of x, y, z through the point P naught is, well, let's think about it. Del f is going to be playing the role of that orthogonal vector to my plane, and that's the vector that is the partial with respect to xi plus the partial with respect to yj plus the partial with respect to zk. And I am thinking about evaluating these partials at the point x naught, y naught, z naught. I'm just trying to shorten up the notation a little bit. And it passes through the point x naught, y naught, z naught. So my tangent plane, fx times x minus x naught plus fy times y minus y naught plus fz times z minus z naught is equal to 0. That's the equation of a tangent plane. Just thinking about our lesson on finding the equation of a plane, I needed a vector normal that gave me an a, b, and a c, and then those became the coefficients in front of these terms. So that's how we can always find a tangent plane to a level surface. So a good question is, what if I wanted to find a tangent plane to a surface defined as a function on two variables? Z equals x squared minus y squared. This is my hyperbolic paraboloid. Assuredly, a nice function like this, if I identify a point on it, I should be able to find a tangent plane. Well, this is where I remember that every surface that was defined as a function on two variables is really a level surface to a function on three variables. And so I can apply the same definition, though things get a little easier, right? The partial with respect to x might be interesting. The partial with respect to y might be interesting. But since this used to say z equals, everything I would define like this always has this minus z. And so the partial with respect to z would be minus 1 in every case that I was looking at. So in this simplified case, instead of a partial with respect to z here, you'll see a minus 1. Now, truthfully, I always think about this formula, and I just rewrite things as a level surface. In your textbook, you will see a separate formula written down for this case. Where that partial with respect to z is just replaced with the minus 1. And you can do this however you want. You can memorize this second formula, or you can do what I do and just rewrite things in that form of a level surface. Okay, so in our next video, we'll do a couple examples of finding tangent planes to surfaces.